Hi everybody, my name is Zhang Fan from Delta Networks. So today we're going to do some speech regarding the open source effort from Delta. We have three speakers. First one is myself, and then Joe Levesque from Microsoft. The third one is Tiffany, one of our senior software engineers. Now, Delta is a $1 billion ODM business company, mainly focused on the switches. And currently, we're moving into this open source domain and supporting and helping the disaggregated solution as well as the SDN solution. Now, the project currently we're helping and working on, the first one is the Sonic, which is from the Microsoft. And the Sonic itself is, you guys probably understand, it's a full-blown routers. And we have a full demo at our booth, D4. After the speech, I welcome everybody to come visit us for the Sonic demo, as well as the Stratton, which is a new project. Basically, itself is a P4 platform. Now, next, I'm going to hand over to Joe Levesque from Microsoft to introduce our Sonic new platform API.
Thanks, John. Thank you. So, developing a platform system, platform control system for a cross-platform operating system such as Sonic presents many challenges because Sonic runs on dozens of hardware platforms, and each platform has a different array of peripheral devices and different locations on the device itself. So the current platform API in Sonic, we have a series of daemons that run, and each controls one specific piece of hardware. We have a daemon to control transceivers, a daemon for fans. So everything's segregated by device type. And the current system, we have an API of individual plugins which interface between the actual hardware level and the daemons themselves. So this API is the layer that the vendors have full control over to implement their interface to their hardware. The current system is a little messy as Sonic has grown and has supported more platforms in different configurations. We found that all these different plugins are a pain to keep maintained because they're in different locations. So the new platform API that we're designing now is a more object-oriented, structured base class approach, and we'll have a hierarchical design which will allow for everything to be contained in one location and make maintenance easier as we go on. So the vendors will need to be made aware of new plugins with our current system because they all live in different places. It's hard to know that something new has come about. This new system will allow vendors to more easily manage their peripheral interaction. So yes, this is an object-oriented hierarchy that we're implementing. We have one basic Python package, which is will contain all the base classes for each of the peripheral devices. Vendors will implement one class based on, or one package based on that package, and implement each of the classes therein. So the new package will run within the platform monitor Pmon Docker container, and this will contain all the platform interaction in one Dockerized container, keeping not only the API itself together, but also all of the management themselves. So this here is an overview of the new API. We have a device base class, which everything will inherit from. And as you can see, we have a chassis base, which implements much of the device base class. And then from there, we have all of these other components, which are included on the chassis itself. And in this way, as you can see, the hierarchy really helps for modular chassis. When we have a modular chassis, you can have SFPs, you can have fans living on a separate part of the chassis itself, not on the main chassis, but on a module, a line card that's inserted. And this new system will allow you, the new platform API will allow you to actually step through, and you'll be able to see exactly where all your hardware lives on basically this will be like a virtual hardware tree of your platform. So this should make management of platform hardware much easier in the future. Thank you. Thank you, John.
Thank you. Many thanks to Joe introduction to the new Sony API. Now, Delta, based on the Sony new platform API, we redesigned our platform. We understand the traditional way of doing the Sony platform is through the CCFS and then the kernel driver. It's hard to extend and also hard to do the runtime or the init time reconstruction of the platform. For example, we have certain hardware changes. So Delta redesigned the overall platform based on the new Sony platform API using the more flexible and adapted Delta Delta platform API, DP API. And we also provide a DP API DAG extension to our new platform. Underneath the driver is their own user space driver. Now the major component is the Delta platform API. Let me briefly introduce the design and also the beauty of the DP API. We call that DP API. Now the DP API itself, the driver is constructed during the init time. What does that mean? That means we chop all the driver into the pieces and we reuse the driver which is common to all the drivers. That increases our software reusability and easier to scale it up. So that's a new design of our new platform layer. Now inside this DP API, we also have the diagnostic extension, which means we are able to support the runtime diag. So that's a beauty of the new Delta platform API. Now next, I'm going to do some demo. This is Delta switches. We have 3 AG9032V1 Tomahawk switches running the Sonic, and I have 2 iBGP sessions set up. On the right-hand side is the Delta 119 running the iBGP AS65123, and on the left-hand side is the Delta 123 running another iBGP instances. And then we will see the iBGP adjacency established, and then I'm going to do the pin session and to each direction to pass on the traffic. Because each side of iBGP, they will announce the reachability, i.e. the route, the network reachability behind them. So I can do the pin. And then for the new platform API, we implement a SFP monitor CLI, which is capable of doing the real-time transceiver monitoring. And then I'm going to pull the transceiver on one side. And then from the real-time transceiver monitoring, you understand on the right-hand side, the transceiver is broken. And then we fix the transceiver. Of course, the traffic stopped as well, right? And then after we identify the problem of the transceiver problem, and we fix the transceiver problem, the route relearn by each other, and then the traffic resume. Now, here on the right-hand side, Delta 119. I'm showing the BGP neighbor. We understand that on the right-hand side, right? The iBGP session established, and the other side router ID is 117.123.1.1, and the update has been exchanged for 4 updates. And then when we show the IP route, we'll see the BGP routes. You see that BGP route I learned from the neighbor, which is a sub-network now route. I changed the Quagga inside the BGP container to announce the network route. Then I'm going to start the traffic. I'm going to start the traffic from Delta 119 to Delta. This is the Quagga configuration, by the way, in the BGP container. Okay, now start the traffic to the other side. Now at the Delta 123, here's a iBGP neighbor I learned. Oops. Oh, anyway. Sorry. And we saw that Delta 1, 2, 3, that router on the left-hand side, BGP router on the left-hand side also received the 4 updates from the right-hand side, Delta 119. And the show IP route showing I learned a BGP route from the Delta 119. I'm going to start the traffic, and here's the Quagga configuration inside the BGP container. Next, I'm going to start the transceiver monitor, real-time transceiver monitors software I wrote. So I'm monitoring Ethernet 40, interface Ethernet 40, which is port 11. Now, you see we're able to read all the DOM information from the transceiver on the right-hand side, Delta 119, and then here's all the DOM information. If you understand, if you're familiar with the transceiver DOM information. Right? Now, on the left-hand side, Delta 123, same port number 11, Ethernet 40. I'm also doing the real-time transceiver monitoring. Now, next, on the switch on the right-hand side, the Delta 119, I'm going to pull out the transceiver from the switch port number 11. You see, after I pull out the switch, the transceiver on the right-hand side, Delta 119, the monitoring software tells you that SFP, the double EEPROM we're not able to see the double EEPROM, and also not able to see the transceiver, and then the traffic stopped as well. Now, next thing I'm going to do is I'm going to plug the transceiver back into port number 11. On the left-hand side, it's fine. On the left-hand side, the transceiver is okay, but right-hand side transceiver is broken. So we understand the problem is on the right-hand side, the Delta 119 transceiver port 11. Now I'm going to plug in the transceiver back, and then after transceiver I plug back in, the IBGP route will learn each other IBGP route, and then the traffic resume. You see the transceiver now is back online, and the traffic is back as well. I'm not going to show you the BGP route. I will hand it over to my speaker, to the next our team member, Tiffany, for Stratum presentation. Thank you.
Okay, thank you, John. So besides SONiC, Delta also involved in another open source project, which is Stratum. So this is overall architecture of Stratum. Delta's involvement is in the orange box in the middle, the platform manager. So the platform manager is a software component in Stratum, manage platform peripherals, such as SFP, fan, temperature sensor, power supply, LED, and so on. So this is a more detailed diagram about platform manager. So on top of the box, in the darker blue box, that's a platform manager. And as you can see, there are multiple software components in platform manager. So on top, there is ONLP HAL. It's a layer that exposes platform functionality to the rest of the Stratum layer. So in the middle, there is a PHEL database. It's mainly a database store, hardware, and system attribute. So there is a component called event handler. It mainly provides event notification of any hardware device status changes in your system. So there are a few data sources. As you can see, we have SFP data source, fan, LED. We also have PSU and thermal. So each type of data source really corresponding to one type of your peripheral. So the data sources is mainly to manage your hardware attributes. So the data sources retrieve hardware attributes from hardware mainly through another layer. We call it ONLP API wrapper layer. So this layer is the one that make call to ONLP. So it understands ONLP specific detail. It also hides the ONLP specific detail from the rest of the Stratum component. So as you can see, in Straton, we leverage ONLP to provide platform functionality. And the version we use is ONLP v2. So within ONLP, Delta's implementation reuse the Delta Platform API to access hardware. So as you can see here, this is another example Delta is using Delta Platform API to provide platform functionalities. So with this Delta Platform API, different applications can access our hardware peripheral using the same method. So that's it. We do have a Straton demo in our booth. Please come to our booth to see the live demo. And our booth is in D4. Okay, thank you.